Our next speaker came all the way from Spain to participate in this session, Dr. Maria Lopez. She is a researcher with CMAT at the Spanish Ministry of Economy and Competitiveness. She has more than 20 years of experience in internal dosimetry. Her representation is EURADOS Intercomparison of measurements of Am-241 in 3 skull phantoms.
Okay, good afternoon. This work is a result of a joint collaboration of EURADOS, the European Radiation Dosimetry Group, and USTUR for an intercomparison exercise on measurement of americium in 3 skull phantom. It was organized by Working Group 7 on internal dosimetry of this European organization. And the 3 phantoms that were in part of the exercise are shown in the slide. So we had 12 laboratories, 10 from Europe and 2 from North America. The transport of the 3 phantoms started in Germany, then went to Czech Republic, Slovakia, Belgium, France, Spain, UK, in Finland, in Europe, and finally went to North America to Human Monitoring Laboratory in Canada and to Richland, precisely very close to here, to Tim Lynch Laboratory. So the main objective of this measurement exercise was to compare counting efficiency and fixed position over each head phantom, the estimation of the activity, if possible, by the participants, and to compare the phantom itself and to check if these phantoms could be considered as calibration source for monitoring americium in real head bone. Parallel to this measurement exercise, we had the idea to also launch a Monte Carlo intercomparison with the voxel version, the voxel representation of these 3 skull phantom. And it was, I think, a good idea and success. We will see the result. So americium, as all of you know, is a very radiotoxic radionuclide, bone surface seeker and long-lived radionuclide, and usually is evaluated from in vitro monitoring of excreta sample by alpha spectrometry, but also maybe used for the detection of the 59 in vivo maybe also evaluated by in vivo monitoring through the detection of the gamma emission of 59.5 keV in lungs and bone. And with reference with bone monitoring, the preference is the knee of the skull because of less attenuation of the photons using Germanium detectors and gamma spectrometry. But in this case, for in vivo monitoring, appropriate anthropomorphic phantoms simulating the rotation of americium in this part of the body are required for calibration, and not always are available. So the BFS phantom was the first of the skull that we used for this exercise. It was fabricated by New York Medical Center. It's a real human bone artificially labeled with americium in its inner and outside sides around 1990. And the interior of the phantom was filled with paraffin wax, and the outside was covered, the bone was covered with wax of 6 millimeters, and the activity was around 5,000 becquerels of americium corrected to 2012. Then the USTUR phantom was part of this case number 102, the first whole body donor, and half of the skull was really contaminated, and it means the americium is in the matrix, in the bone matrix, and the other half was completed the phantom with real bone, but from non-contaminated person. And the skull was filled and covered with tissue equivalent material. And here the activity corrected to 2012 is around 300 becquerels. Finally, this simple phantom was constructed especially for this exercise. It's a hemisphere of equivalent wound and tissue material representing just the top of a human head with an activity around 1,000 becquerels. And the main issue of this phantom was the validation of counting efficiency obtained with Monte Carlo study for a simple counting geometry. So task 1 of the exercise was required is to obtain the counting efficiency in different parts of the phantom. And counting efficiency is easily obtained just dividing the count rate by the activity for the emission of 59.5 keV of the americium. For the hemisphere phantom, it was just required the position over vertical position. And for the USTUR phantom and the BFS phantom, several positions were defined in the protocol looking at the best count rate. So the distance was just 1 centimeter, detector phantom. And you can see here the participants, all of them use germanium detector. All of them are just from 2 commercial companies, very well known, Canberra and Ortec. And which was of interest for us was to know the active area of the germanium crystal and the diameter to check the impact of the size of the detector in counting efficiency. Important also to see that the window of the most of detectors are for carbons, but in case of participant 18 is from aluminum. We will see the impact of this issue in the result. So for the measurement of BFS phantom, you can see in the bottom of the slide the 5 position that was checked, and the maximum efficiency was found in the position 3. And in the graph, it's plot the variation of counting efficiency with the diameter of the detector. And it was found that participants with the same diameter that have similar detector have similar counting efficiency. That, of course, is the efficiency increases with the diameter of the detector. And for the 60 millimeter detector, we have a strange low value of counting efficiency, and this is because these participants have the aluminum window in the detector, and it was a big impact in the counting efficiency. Regarding the USTUR phantom, remember that only half of the phantom was contaminated, so here the dependency of the counting efficiency with the diameter is more important than in case of BFS phantom, and the maximum efficiency was obtained in the right side of the school where was the contaminated half. And the second task of the exercise was, in case of the participant has his own calibration phantom, to calculate activity using the calibration factor obtained independently of the phantom, of the measurement of the phantom of the intercomparison. So only 6 participants provided this result, and which is very interesting is half of them used Monte Carlo calibration to calculate this activity. So you can see here the calibration phantom used by the 6 participants. So the first one used Monte Carlo calibration with the 38-year-old woman, voxel phantom obtained from CT images. The second one is also Monte Carlo calibration using ICRP reference man and woman. The next, using University of Cincinnati phantom, this was a physical phantom, physical calibration. Next one used Hickman school phantom, fabricated by the New York Medical Center. The 5th was used voxel phantom for Monte Carlo, and finally the 6th, the Cohen phantom for a physical calibration. And the result are shown here. There is a quite important discrepancy in the result of the ratio of the estimated activity with reference to the true value. All of them overestimate in the case of BFS phantom. This is due because BFS is a small head, so it means that it's not fitting well with calibration regarding an adult, typical adult reference person. And regarding USTUR, the results are not too bad, but remember, it's only half contaminated, so it's tricky. So in parallel with this exercise, it was launched by the EURADOS website, the Monte Carlo modeling version for this in vivo monitoring of American school phantom. And here the participants could download the modeling of detector and the voxel phantom. So 3 tasks were identified, increasing difficulty. First, the model of the detector and the voxel phantom was provided. They just had to proceed with Monte Carlo calculation. The second one, the participant have to perform the modeling of his own detector and using the voxel phantom for BFS and USTR in the counting geometry defined in the measurement exercise. And the task 3, just modeling their own counting geometry when they use it for measurement real contaminated people. So this is the result of task 1. This the objective was to check tools and skills of the participants. Only 4 of them, 16 participants answered in this case. Only 4 of them had some outlier result, but after discussion with the organizer, they corrected the result. And all of the counting efficiency obtained by Monte Carlo were in good agreement in less than 10% with reference to the measurement value. It's also the spectrum, you can see in the right side of the slide, was quite good agreement, especially for the peak of 59.5 keV with some problems in the simulation of the X-ray below 20 keV. Regarding task 2, it was a good agreement between the measurement spectra versus the simulated spectra, and ratios of simulated versus measurement efficiency was very good as well. In general, around 6% and maximum 12%. So this was a good demonstration of the utility of these Monte Carlo methods for simulating in vivo monitoring geometries. Regarding task 3, here we had the opportunity to check how people manage around the world for measurement American in Bonn, in the school. And also we got a very good agreement between all the participants with the discrepancies less than 7% with reference to the measurement value. So finally, as conclusion, EURADOS Intercomparison, Measurement, and Monte Carlo Simulation were launched with the objective of providing tools to participants to evaluate the variability of counting efficiency and assess activity due to the use of different school phantom. Regarding measurement intercomparison, was a good agreement between the 12 participants with a similar result with similar detector. And regarding the task 2, when they calculate the activities, users their own calibration phantom showed discrepancies up to a factor of 3.4. It means that the difference between the phantom, the calibration phantom, and the measure phantom has a big impact in the calculation of the activity, so of course in the dose. Regarding Monte Carlo intercomparison, just to say that was a good agreement between both approaches, the Monte Carlo counting efficiency and spectra, comparing with measurement. And the conclusion also was that the 3 phantoms differ in shape, size, and weight. No one fulfills the requirement of a standard calibration source for the calibration of Germanium detectors, for the measurement of harmonics in the school of standard male workers. So the BFS phantom is too small. The USTUR only have half part contaminated, and the SCR was too simple. So it put attention here, the importance also to have these tools of Monte Carlo and voxel phantom that cover when there is lack of physical phantom appropriate for calibration and so for monitoring. So thanks for your attention. Just to finish, to say that acknowledge to participants, especially to Sergey, who provided the phantom to Pedro Nogueira, who coordinated the measurement exercise, Thomas Brad, the Monte Carlo exercise, and the rest of participants. And after this exercise, a Monte Carlo a training course for application of Monte Carlo methods to in vivo monitoring was organized by EURADOS and Karlsruhe Institute of Technology. A new edition will be organized very soon. We will keep you informed in case you are interested. And other exercise using Monte Carlo methods for simulated in vivo monitoring was organized in the past. Especially, I would like to stress the one using the USTUR leg phantom, also provided by Sergey, and you have the 3 publications associated with the exercises. Okay? Thanks for your attention. Okay.
Any questions?
Maria, when I was looking at those ratios, looks like the USTR phantom is the best, at least to me.
Yes.
Okay. So, but my question is, so also USTR has the lowest total activity in the skull. Is there any chance that, because it was about 300 becquerels, right? When the BSF has about 6 kilobecquerels, so it's 20 times difference. Is there any dependency on efficiency on just because of the different activity, or how they participant measured? So basically low activity and high activity.
No, I think.
Sorry.
I think the 5,000 becquerels or 300 becquerels is not a big deal, because detection limit could be around 20 becquerels, something like that. Yeah, but I think the big impact is in the size and the shape of the phantom, especially because USTUR phantom could be the best. If the 2 halves are contaminated, there would be, I think, a good calibration phantom. But BFS is too small. We check a lot this issue, and it's clear that there's a big impact in the counting efficiency. This is the main reason.
Any other questions? Oh, good. Yeah.